Welcome to our exploration of ML feature store architecture. We'll delve into both real-time and batch features, understanding how these components work together in complex machine learning systems.
Imagine you're building a real-time fraud detection system. Every transaction needs to be scored in milliseconds using hundreds of features. Some features, like the user's recent transaction history, require real-time computation. Others, like demographic information, can be pre-computed in batch. Without a proper feature store, you'll end up with duplicated code, inconsistent feature definitions, and massive latency issues that will render your fraud detection system useless. We'll explore how a robust feature store architecture solves this. A naive approach might involve directly querying your operational databases for features at inference time. This quickly becomes a nightmare. Imagine multiple models, each requiring different feature combinations, all hammering the same databases. The increased load will cripple your application's performance. Furthermore, ensuring consistency between training and serving becomes incredibly difficult. If your training data uses a different feature calculation logic than your serving code, your model's accuracy will plummet in production. This is the classic training-serving skew problem. Let's consider a slightly better but still flawed approach, pre-computing features in batch and storing them in a dedicated feature database. While this solves the operational database overload issue, it introduces new challenges. How do you handle real-time features that depend on the latest transaction data? Recomputing all features in batch every few minutes is often too slow for real-time applications. Additionally, managing the data pipeline for batch feature computation can become complex and difficult to maintain, especially as the number of features grows. The solution is a well-designed feature store architecture that supports both real-time and batch feature serving. This involves a combination of online and offline data pipelines, a dedicated feature serving layer, and robust data consistency mechanisms. We need a system that can handle low-latency feature lookups for real-time inference, while also providing a reliable source of features for batch training. This architecture needs to be scalable, maintainable, and ensure feature consistency across all stages of the machine learning lifecycle. Let's dive into the details. Let's zoom in on the right path. When a new feature value arrives, it's crucial to ensure that the data is persisted reliably and made available for both real-time and batch consumption. The first step involves routing the incoming feature data through an API gateway to our feature ingestion service. This service is responsible for validating, transforming, and routing the data to the appropriate storage backend. A key component here is a message queue, typically Kafka, which acts as a buffer and decouples the ingestion service from the downstream storage systems. This decoupling is essential for handling spikes in traffic and ensuring data durability. Kafka partitioning is critical for scaling the right throughput. We can partition feature data based on the entity ID, ensuring that all features for a specific user or item are written to the same partition. This partitioning strategy optimizes read performance for real-time feature retrieval. Within Kafka, each partition is replicated across multiple brokers for fault tolerance. From Kafka, the feature data is then consumed by two separate pipelines, a real-time pipeline and a batch pipeline. The real-time pipeline focuses on low-latency feature retrieval, while the batch pipeline is optimized for offline training and analysis. We're essentially creating two parallel data streams from the same source of truth. For real-time features, we often need to serve feature values with millisecond latency. This requires a low-latency storage solution, typically a key-value store like Redis or Memcached. The real-time pipeline consumes feature data from Kafka and writes it to the key-value store. To optimize read performance, we can use techniques like feature pre-computation and caching. Feature pre-computation involves calculating feature values ahead of time and storing them in the key-value store. Caching involves storing frequently accessed feature values in a cache layer in front of the key-value store. This cache layer can be implemented using Redis or Memcached, providing even lower latency access to feature values. Now, let's look at the batch pipeline. For batch features, we need a storage solution that can handle large volumes of data and support complex analytical queries. This is typically achieved using a data warehouse or a data lake, such as Hadoop or Cassandra. The batch pipeline consumes feature data from Kafka and writes it to the data warehouse. The data is typically stored in columnar format, which is optimized for analytical queries. From the data warehouse, feature values can be extracted and used for model training and offline analysis. The choice of data warehouse depends on the specific requirements of the application, including data volume, query complexity, and cost. To handle the asynchronous processing of batch feature generation, we leverage a message queue like Apache Kafka. The data ingestion service publishes raw data events to Kafka topics. These topics are partitioned to allow for parallel processing by multiple feature engineering workers. These workers subscribe to the Kafka topics, consume the raw data, and perform feature transformations. The transformed features are then persisted to the offline feature store, typically a data lake like Apache Hudi or Iceberg, optimized for analytical queries. This design decouples data ingestion from feature computation, enhancing system resilience. Within the batch pipeline, feature transformations are often computationally intensive. To accelerate this process, we use distributed computing frameworks like Apache Spark or Dask. Spark allows us to process large datasets in parallel across a cluster of machines. The feature engineering logic is expressed as Spark jobs, which are submitted to the Spark cluster for execution. Spark reads the raw data from the data lake, applies the transformations, and writes the resulting features back to the offline feature store. This parallel processing significantly reduces the time required to generate batch features. Now let's discuss the caching layers for both real-time and batch features. For real-time features, we use an in-memory cache like Redis or Memcake to provide low-latency access to feature values. When a request arrives for a feature, the feature store first checks the cache. If the feature is present in the cache, a cache hit, it is returned immediately. If the feature is not in the cache, a cache miss, the feature store retrieves it from the online database, stores it in the cache, and then returns it to the client. This caching strategy significantly reduces the load on the database and improves response times. For batch features, caching can also be beneficial, especially for frequently accessed features. However, the caching strategy differs slightly. Since batch features are typically pre-computed and stored in the offline feature store, we can use a distributed cache like Apache Ignite or a cloud-based caching service like AWS ElastiCache. This cache is populated with the most frequently accessed batch features. When a request arrives for a batch feature, the feature store checks the cache first. If found, it's returned. Otherwise, the feature store retrieves it from the offline store and potentially caches it for future requests. The cache invalidation strategy is also important to consider. Asynchronous processing plays a vital role in handling real-time feature computations, especially when dealing with complex transformations or external API calls. We leverage message queues like Kafka or RabbitMQ to decouple feature computation from the online serving path. When a new event arrives, it's immediately published to the message queue. Feature computation services consume these messages asynchronously, compute the features, and store them back in the feature store. This prevents long-running computations from blocking the online serving layer and ensures low latency for serving real-time features. Caching is crucial for both real-time and batch features to minimize latency and reduce the load on the underlying feature store. For real-time features, we often employ in-memory caches like Redis or Memcake to store frequently accessed feature values. These caches sit in front of the feature store and provide extremely fast access to the most popular features. We can use techniques like cache invalidation or time to live (TTL) to ensure that the cache remains consistent with the underlying data. Caching strategies must be carefully designed to balance performance and data freshness. Now let's explore advanced caching strategies. For instance, a write-through cache updates both the cache and the underlying database simultaneously, ensuring data consistency but potentially increasing write latency. On the other hand, a write-back cache updates only the cache initially, and the database is updated asynchronously, improving write performance but introducing a risk of data loss if the cache fails. The choice between these strategies depends on the specific requirements of the application and the trade-offs between consistency and performance. Consider using a multi-layered cache for optimal performance. Maintaining data consistency between the cache and the feature store is a critical challenge. Cache invalidation strategies such as TTL-based expiration or event-driven invalidation help ensure that the cache reflects the most up-to-date information. For batch features, we can use techniques like versioning or periodic cache refreshes to maintain consistency. Furthermore, implementing monitoring and alerting systems to detect cache staleness or inconsistencies is crucial for maintaining the reliability of the feature store. These are important considerations for a robust feature store architecture. Now, let's pivot to the critical aspect of infrastructure management for our feature store. A robust infrastructure is paramount to ensure reliability, scalability, and performance. We'll explore key components and strategies to build resilient and efficient feature store environment. This includes monitoring, alerting, and automated scaling to handle varying workloads. Proper infrastructure also allows for easier debugging and root cause analysis when issues arise, minimizing downtime and maximizing feature availability. Consider containerization and orchestration technologies for deployment. For monitoring, we integrate Prometheus, a powerful time series database, to collect metrics from all components of the feature store. These metrics include CPU utilization, memory consumption, network latency, and feature retrieval times. Prometheus allows us to define alerts based on thresholds, notifying us of potential issues before they impact performance. Grafana is then used to visualize these metrics, providing a clear and intuitive overview of the system's health. Real-time dashboards show feature usage, latency, and error rates, enabling proactive monitoring and troubleshooting. Automated scaling is crucial for handling fluctuating workloads. We can leverage Kubernetes' horizontal pod autoscaler to dynamically adjust the number of feature store instances based on CPU utilization or request rates. This ensures that the system can handle peak loads without performance degradation. Furthermore, we can implement a circuit breaker pattern to prevent cascading failures. If a particular feature retrieval service becomes unhealthy, the circuit breaker will trip, temporarily redirecting traffic to healthy instances or returning a cached response. Another key element of robust infrastructure is logging and tracing. Centralized logging, using tools like Elasticsearch, Logstash, and Kibana ELK Stack, allows us to aggregate logs from all components, making it easier to diagnose issues. Distributed tracing, using tools like Jaeger or Zipkin, enables us to track requests as they flow through the system, identifying bottlenecks and performance hotspots. Together, these tools provide comprehensive visibility into the feature store's behavior, facilitating efficient troubleshooting and optimization. Think about correlating logs and traces to pinpoint problems faster. To further enhance our feature store's resilience, we can implement circuit breaker patterns at the service level. Circuit breakers prevent cascading failures by halting requests to unhealthy services, giving them time to recover. This is crucial in a real-time feature serving environment where low latency is paramount. We can use libraries like Hystrix or Resilience4j to implement these patterns within our microservices. The circuit breaker monitors the health of the downstream service based on metrics like error rate and latency. If the error rate exceeds a certain threshold, the circuit breaker trips, preventing further requests from reaching the failing service. Now that we've addressed resilience, let's examine feature retrieval optimization. For real-time feature serving, minimizing latency is critical. We can leverage techniques like caching and pre-computation to speed up feature retrieval. For instance, frequently accessed features can be cached in a distributed cache like Redis or Memcached. Pre-computing features during batch processing and storing them in a low-latency data store can also significantly reduce retrieval time. We need to carefully select the right data structures and indexing strategies for our feature store to ensure efficient query performance. Bloom filters can be employed to quickly determine if a feature exists in the store before performing a more costly lookup. Next, let's consider feature versioning and governance. In a dynamic ML environment, features evolve over time. It's essential to implement a robust versioning system to track changes to features and ensure reproducibility. We can use techniques like feature lineage to track the origin and transformation of features. This is crucial for debugging and auditing purposes. Furthermore, we need to establish clear governance policies for feature creation, modification, and deprecation. This helps maintain data quality and prevent inconsistencies. A central feature registry can be used to store metadata about features, including their version, description, and owner. Finally, let's address security considerations for our ML feature store. Access control is paramount to protect sensitive data. We need to implement role-based access control, RBAC, to restrict access to features based on user roles. Encryption is also crucial to protect data at rest and in transit. We can use techniques like data masking and anonymization to protect personally identifiable information, PII. Regular security audits and penetration testing should be conducted to identify and address vulnerabilities. Integrating the feature store with existing security infrastructure, such as identity providers and security information and event management (SIEM) systems, is also essential. Ensure compliance with relevant data privacy regulations, such as GDPR and CCPA. To handle increasing data volumes and query loads, the feature store needs to scale horizontally. This involves partitioning feature data across multiple nodes in the underlying databases and caches. Implement sharding strategies based on feature IDs or user IDs to distribute data evenly. Utilize consistent hashing for efficient data retrieval across shards. For real-time feature serving, consider using a distributed caching system like Redis Cluster or Memcached to minimize latency. Employ read replicas for the feature store databases to offload read traffic from the primary nodes and improve query performance. Auto-scaling can be implemented for both the feature store components and the serving infrastructure to dynamically adjust resources based on demand. Robust monitoring and alerting are crucial for maintaining the health and performance of the feature store. Implement comprehensive monitoring dashboards to track key metrics such as query latency, data ingestion rates, cache hit ratios, and error rates. Integrate monitoring tools like Prometheus and Grafana to visualize these metrics and set up alerts for anomalies. Define service level objectives (SLOs) for feature retrieval latency and availability, and configure alerts to trigger when these SLOs are violated. Implement automated remediation procedures to address common issues, such as cache invalidation or database failover. Consider using distributed tracing to identify bottlenecks in the feature retrieval pipeline and optimize performance. To summarize, building a robust ML feature store involves several key considerations. First, defining clear feature specifications and data contracts ensures consistency and reliability. Second, choosing the right storage technologies for both real-time and batch features is critical for performance. Third, implementing effective data pipelines for feature engineering and transformation is essential for data quality. Fourth, designing a scalable and resilient architecture is necessary to handle increasing data volumes and query loads. Finally, robust monitoring and alerting are crucial for maintaining the health and performance of the feature store. A well-designed feature store enables faster experimentation, improved model accuracy, and reduced operational overhead. In conclusion, a well-architected feature store is paramount to successful machine learning deployments. By carefully considering the trade-offs between real-time and batch processing, selecting appropriate technologies, and implementing robust monitoring, organizations can significantly improve the efficiency and effectiveness of their ML initiatives. Remember that the specific implementation details will vary depending on the use case and the scale of the data, but the fundamental principles remain the same. Focus on data quality, scalability, and operational efficiency to build a feature store that can support your ML efforts for years to come. This approach streamlines model development, reduces data skew, and enhances overall ML performance.
Like, share, and subscribe to my channel for more AI insights. I'm the Code Architect. See you soon.